We want to spend some time talking about this framework. I'm going to scroll up to the top and I'll show you that we had started out here with this rigorous theoretical synthesis that unifies the provided cortical subcortical neuromorphic engine. So we were working on this before. We've got some sets over here. And we're using the AND, or agentic negentropic dynamics, with the REC, the relational energetics and control master law. And we have the mathematical presentation here, but what I did is I kept the initial planning, and then I did a extension here, and then I did a second extension, and then we have the code. So I kept the history of the development step by step. And so that's going to be available to our partners if you want to learn about this particular negentropic engine. Now, when I'm talking about agentic negentropics, we're being inspired by biological intelligence and its energy parsimony and its intelligence levels. Because, as you know, the human brain actually operates only on about 20 watts of energy, and it's less than a light bulb, right? And yet it does amazing feats of intelligence that no computer has yet come close to being able to emulate. So that's what we're talking about, sort of moving away from legacy machine learning and legacy deep learning into a new paradigm of much more bio-inspired intelligence. Now, what we're looking at here is a sophisticated neuromorphic engine. It's essentially a simulated brain-like system. And again, we've built it up on this theoretical framework called AND plus REC. That being said, you can actually go out to here and you can see that we're just in version 6, version 10 here, but each one of these folders holds a vast array of more than 700 different code bases, and we're taking different approaches to bio-inspired intelligence, many of them, 600 or 700 different scripts, many different approaches. And so we've learned a lot in this. It's been in excess of a year that we've been working on this every day. It's fascinating once you get involved. But I'm going to drill in here. You'll see that there are so many, right? And I'm in the Genesis wave right here, into the advanced, and I'm right here looking at this one, the cortical AND and REC. So that's this one right here. But I did want to give you that background. This is one of many, many approaches. Let's just talk this through. So what we're doing is combining fast reactive processing. That would be like your brain's cortex. And we're combining that with slower adaptive learning and memory. And that would be similar to your subcortical regions. And we're doing this all the time, accounting for energy efficiency. And again, like biological systems. So the goal here is to create a bio-cyber agent that's an artificial intelligence that learns and adapts and behaves in ways inspired by living organisms. We're going to break this complex system down piece by piece. We're going to start from the foundational tools, and we're going to move up to the core engine and the engine's functions. So first off, before we dive into the brain-like engine itself, we need to have some specialized tools. So there's some helper functions that we're going to be looking at. They're going to ensure that the mathematical operations, especially those that involve angles and probabilities, we have to handle those correctly and we have to handle those robustly. And so let's talk about angle management first. So we have a function here called the RAP angle. In our simulated brain, there are certain variables called phasors, and they represent oscillatory activity. So again, think like your brain waves. And these oscillations are described by angles. And the RAP angle function, it ensures that these angles always stay within the standard range, from negative pi to positive pi. It's going to prevent numerical errors, and it's going to make the interpretation of the angles consistent. So example, take the angle 361 degrees. That is actually the same as 1 degree. And so this RAP function, it normalizes cases like that. Now if you build on this, then the angle dist function down here, this calculates the shortest difference between two angles, and that's important for understanding how different oscillating parts of a simulated brain are either out of sync or in phase with each other. And so by handling these angles meticulously like this, it's actually crucial because accurate phase relationships are fundamental to many of the theories of brain function, all the way from sensory processing up to memory recall. Now next we're going to look at these three functions down here. You've got makes this pause, then you've got logit SPD, then you've got the Gaussian K all down here. Our neuromorphic engine, it has beliefs about the world, And these beliefs are represented using probability distributions, especially Gaussian distributions. These are defined by a mean, that's what the system believes, and a covariance matrix, how uncertain it is about that belief. This makes his pos function critical for maintaining the mathematical integrity of those covariance matrices. In the real world, and especially in probability theory, covariance matrices, they have to be symmetric, and that means that they have to look the same if you flip them along their diagonals. And they also have to be positive definite, which means that it describes a valid spread or a valid uncertainty in all directions. So numerical approximations during computation, they can sometimes make the matrix slightly invalid. And this function detects those types of issues, and they actually nudge the matrix back into a valid, symmetric, positive definite form by ensuring all that fundamental spread values, those eigenvalues, they all have to be positive. And so this ensures that the engine's, its internal beliefs always remain coherent, and they always remain mathematically sound, and they prevent any kind of nonsensical results. Now this next one down here, this Logit SPD, you could probably boost the size of this a little bit. Yeah. This calculates a specific value related to the volume or the spread of a probability distribution as it's defined by its covariance matrix. So this isn't just a numerical gymnastics here, it's deeply connected to information theory, and it helps us to quantify the amount of uncertainty or information contained within a belief. And now down here, this Gaussian KL here, it takes the Logit SPD a step further by calculating the Kullback-Leibler, or the KL divergence between two Gaussian distributions. And you can think of KL divergence as an information distance. It basically measures how much one probability distribution is different from another distribution. So if our engine updates its belief, then the Gaussian KL, it tells us how surprising that new belief is compared to the old belief, or how much information was gained in the update. And this is a fundamental requirement for tracking information flow and uncertainty, and it's a concept that is central to many modern theories of brain function, like predictive coding and such. Now next you have this function under this efficient data compression section here. Because biological brains, they don't process every single detail of the world that they inhabit. They're basically masters of compression. They focus on only what's important. And this randomized RSVD function, this is our computational answer to compression. It's a method for finding the most important patterns or the most important components within any large data set. It finds it very quickly, and this is especially when the data set is too massive to handle directly. So instead of exhaustively analyzing every piece of data in the set, random RSVD, it uses smart random sampling to get a good estimate of the data's core structure. Of course, this is vital for the engine's ability to reduce complex snapshots of its internal state or of its environmental observations, to reduce them into their most salient features without losing too much critical information. And this process is directly related to the model reduction and certification aspect of the AND-REC theory, and that's allowing the engine to remain computationally efficient while at the same time dealing with potentially high-dimensional neural activity. Alright, with our foundational tools in place, we now have to build the core capacities of our BioCyber agent, how it remembers, how it predicts, and how it manages its energy budget, right? So its core capabilities. Just as humans remember specific events like episodes, anything that happens in our lives, these are episodes we remember, so too our A&D engine has an episodic store. So you'll see that the class here, the episodic store class. This class simulates a form of episodic memory capturing patterns. So think of distinct states of the fast cortical-like activity, along with contexts such as their strength or salience, maybe a label, maybe a time step. So when this memory system reaches its capacity, then it makes a biologically plausible decision. It replaces the oldest or the least strong memory with a new memory. So this reflects how biological memory systems are resource limited, and they prioritize the more salient or the more recent experiences. The inclusion of sparsity, meaning Not all parts of the pattern are stored or attended to equally. This further mirrors biological efficiency because brains often use sparse encoding to represent information. So this memory manifold, it provides the agent with a personalized history. It enables learning and it enables contextual behavior. So next down here you're going to see this RLS predictor. Let's talk about that. A hallmark of intelligent systems, especially biological systems, is the ability to predict the future. It's axiologically a very high value capability. So the RLS predictor class, it embodies that capability, that predictive capability, by implementing a recursive least squares algorithm, or RLS algorithm. Now this is powerful adaptive learning. It's a method that continuously builds a model of how the system's features derived from the fast brain activity, how those features evolve over time. And it consistently updates its internal model based on new observations. It weighs the recent information more heavily using a forgetting factor. And this allows the engine to learn the underlying dynamics of its own states or of the environment around it. So it acts as the Koopman RLS predictor mentioned in the theory from above, and it consistently generates forecasts about what's likely to happen next. And that predictive capacity is central to how biocyber agency, how it participates and how it reacts to its environment, minimizing prediction error, which is a core tenet of predictive processing theories in neuroscience. Prediction error. Now, we also have what we call a Landauer book, and this is about metabolic efficiency, because biological brains are incredibly energy efficient. Our neuromorphic engine incorporates this principle through the Landauer book class, which is tracking a metabolic cost of processing any information. And this is inspired by Landauer's principle. It's a fundamental concept in physics. Basically, it states that erasing information, like making a system more certain about something or discarding old beliefs, that type of erasure inherently comes with a minimum amount of energy cost. So the Landauer book function monitors changes in the engine's belief uncertainty, its covariance matrix. When information is effectively erased or reduced, it incurs a cost, which is added to a running metabolic budget. And if the budget is exceeded, then the system dynamically adjusts an internal Lagrange multiplier. That's a penalty factor. And that makes the future information erasure more expensive. And this encourages the agent to be more conservative with its information processing, learning to make efficient use of its computational resources. So that explicit Landauer bookkeeping and the KKT-like dual adjustment, that's a novel way to integrate thermodynamic constraints directly into a neuromorphic model, which in turn fosters more biologically realistic and resource-aware intelligent behavior. So let's talk about the engine's architecture and dynamics down here. This is the Andrack Neuromorphic Engine version 3. And this is the core class that brings everything together. It orchestrates the complex interplay of the fast cortical dynamics and the slow subcortical learning memory, and also the energy management. So you have an init function here, because when you create the Andrack Neuromorphic Engine object, when you create that object, it's like constructing a brain just out of thin air here. We have to define its hierarchical structure. We have to define the level sizes for different layers, the cortical areas, and then there's a number of slow nodes. Those are the subcortical-like units, the DT, the time step for simulation, and also various parameters for memory, for prediction, for energy. So it sets up the fast phasers here, and that's the oscillatory activity, and then their associated momenta, their rates of change, their masses, their inertia for each layer. Then it also initializes the slow Bayesian beliefs, their means and covariance matrices, and the episodic store, and the RLS predictor, and the Lambda book. The episodic store, the RLS predictor, and the Landauer bookkeeping, and that all has to be set up. Before the predictive system can learn, it needs to understand the language of fast oscillatory activity. So these encoder functions, they translate the raw phaser states into meaningful features that the RLS predictor can use. So if you notice this, you've got this raw feature from complex. Down here, this converts the complex numbers representing phasors into a format that's suitable for the predictor, potentially extracting frequency patterns. And then you have this group average encoder here. This is particularly interesting. It addresses a challenge in intelligence, which is recognizing a pattern regardless of any minor shifts of the transformations. So imagine recognizing a phase whether it's slightly rotated or it was shifted in your field of vision. You can still recognize the face, right? Well, this function mimics that by averaging features from multiple slightly transformed versions of the input phasor. This creates invariant features, representations that are robust to irrelevant changes, and that directly relates to the equivariant encoder and the symmetry quotienting concepts in the theory. So this bio-inspired approach, it enhances the robustness of the agent's internal representations. So for predictive control, we need the update predictor and then predictor forcing. So this is the heart of the predictive engine, and it lies within these two functions. Let's talk about the update predictor. It's taking two consecutive snapshots of the fast activity. It extracts their invariant features and it feeds them to the RLS predictor. And this continually refines the engine's model of its own dynamics. So it's always learning how its state transitions from one moment to the next. Then the predictor forcing down here, it uses this learned model. It asks the RLS predictor, it says, hey, given my current state, what do you predict my next state should be? And the difference between the actual current state and the predicted next state generates a forcing term. That's essentially a top-down signal. And the signal acts as a small impulse on the fast cortical-like dynamics, gently nudging those dynamics toward the predictive future. This is the metroplectic forcing in action, where the slow predictive brain, the subcortical-like brain, it guides the fast reactive brain, the cortical-like brain, to minimize prediction error. So let's talk about those fast dynamics, the local engine down here with this compute gradu fast. The fast cortical-like layers, they operate on their own local rules. And this compute gradu fast, it calculates the gradient of potential energy for these oscillating units. Think of it as determining the direction of steepest descent in an energy landscape, but for each independent phasor. So this gradient descent, it depends on the phasor's current state, its interactions with immediate neighbors, like forming a ring-like connection, and also its tendency to return to its set point. This function defines the Hamiltonian, or the conservative generator of the system, driving the rapid local interactions that characterize cortical activity. Let's talk about robust belief updates down here. We've got this solve inner QP mean here. The slow subcortical-like system updates its core beliefs about the world through the proximal belief update function, which is actually down here. What this function does is it takes aggregated observations from the fast layers, like how fast activity summarizes the current situation, and it uses them to refine the probabilistic beliefs, which are the means and the covariances. And the proximal nature of the update means that the beliefs won't jump wildly, but they evolve steadily, maintaining their numerical stability. Now optionally, if the advanced optimization solver OSQP is available, solve inner QP mean can be used to precisely find the optimal mean of a belief, and that ensures the KKT enforcement, which is a rigorous mathematical condition for optimality. But crucially, this function integrates the Landauer book down here to account for the metabolic cost of updating beliefs. If a belief update causes too much information erasure, and if it exceeds the energy budget, the system might partially revert the update, or it might increase the penalty for future erasure, forcing the agent to consider energy efficiency in all of its learning processes. It also incorporates an invariance penalty, encouraging the slow system to learn robust features that don't change drastically with minor variations of input. And this blend of sensory input, prior beliefs, and energy constraints and invariance learning, it allows the slow system to adaptively form stable, efficient internal models of the world. So now we have to start bridging fast and slow. And down here we have this slow project observations function. because the fast cortical layers, they generate a lot of detailed activity, and the slow project observations function. It acts as a crucial bridge, summarizing this high-dimensional fast activity into a smaller, more manageable set of observations for the slow subcortical-like belief system. And it does this by dividing the top layer of fast phasers into segments and by calculating their average activity. And this mimics how complex sensory cortical information might be distilled, and it might be fed into subcortical areas that are responsible for the slower learning, for the decision making, for the reward processing, and things like that. And then we have to do some learning by association. So you might be familiar with the term that neurons which fire together wire together. Yeah, that's a cornerstone of biological learning, or Hebbian learning. And our engine implements a simplified Hebbian update where periodically it just samples 2 existing episodic memories from its episodic store. And if those memories are related, or if they co-occurred, then their features are used to update the RLS predictor. This means the predictive system learns associations between past experiences, allowing it to predict future events based on remembered patterns. And this mechanism contributes to the Hebbian RLS increment, and it helps the agent build a richer associative understanding of its environment. Now we also have to certify the efficiency, because to maintain computational efficiency, especially as the system evolves, as it generates vast amounts of data, the engine must periodically employ this RS-SVD certify function. This function performs that randomized RSVD on snapshots of the engine's history. So think, for example, how fast phasers have changed over time. Then it certifies how accurately this compressed representation captures the original data, ensuring that the model reduction doesn't discard too much important information. If the reduction is certified as accurate enough, it can then be used to refine the internal weights of the engine. That's a process called warm compression, and that makes it even more efficient. And this is a direct implementation of the model reduction and certification aspect, which is crucial for keeping complex neomorphic systems tractable. Okay, let's talk about this step function down here. So we have to think about this step function as the engine's heartbeat, representing one discrete moment in the agent's existence. The step function orchestrates the entire AND-REC master law by executing a precise sequence of operations that mimic the continuous interplay of biological brain functions. So this is where the system comes together here. First, it summarizes the current fast activity into observations for the slow system, which then updates its belief, its means and covariances, using that proximal belief update. And it adheres, of course, to the Landauer energy constraints and the invariance penalties. And this is the dissipative and proximal step. Next, you have the fast cortical-like phasers and momenta that are advancing using this Stormer-Verlet integrator. This is a symplectic Hamiltonian step that's driven by the local energy gradients and the interactions. And then you have predictive guidance down here. The predictor forcing applies a top-down impulse from the RLS predictor, which gently steers the fast dynamics towards the anticipated states. Then, of course, you've got your learning and memory. The RLS predictor itself is updated based on the current and previous states, continuously refining its understanding of the system's dynamics. Then, periodically, the system captures new episodic memories, and it performs Hebbian updates to reinforce associations. These are the update steps. Then there are small thermal stochastic noise, and it has to be injected or scaled by the Landauer's thermal energy, of course reflecting the inherent randomness in physical systems. So the engine also calculates a free energy proxy, which is a measure of the overall system uncertainty and prediction error. And then it updates the KTT multipliers for metabolic and invariance constraints, ensuring the system stays within its energy budget and it learns robust features. Occasionally, it has to perform that randomized SVD certification just to ensure its internal representations remain compressed and efficient, and it can adjust its weights based on these insights. And down here, active masking. This can freeze inactive parts of the system if necessary. It's another form of resource management. So taken all together, the step function here, it It simulates the agent's continuous cycle of perceiving, predicting, learning, remembering, and then adapting, and all at the same time it's balancing its speed, its accuracy, its metabolic cost. And it's the moment-to-moment experience of the simulated biocyber agent. So down here we have the debug report, and of course understanding any complex system is going to require good tools for introspection, right? So the debug report, it provides detailed textual logs and also rich dark themed HTML displays. Those are Plotly displays, and these are especially useful in a Jupyter notebook here. They show the engine's internal states, the statistics, they show warning messages. Of course, it's critical for researchers to monitor the agent's internal workings. This plot free energy, plot top phaser, plot phaser 3D, animate top phaser. These functions lever Plotly to create the interactive dark themed visualizations you'll see down below. And of course these are going to allow us to see any of the abstract concepts like the free energy that evolves over time, or the concrete pattern of the fast oscillatory activity. These are the phasers in 2D and 3D. So we can just scroll down here and you'll see some of these visualizations. Like we say, here's the free energy evolution, here's the 3D scatter of the phasers, here's the top level phasers hardened, and then here's an animation, short animation. You can see it moving slowly there. So the visualizations are definitely helpful. You scroll back up here. Of course, those dynamics, being able to visualize them, it's valuable when you're trying to gain intuition about how that simulated brain is going to behave, and also for debugging any of its intricate processes. And then of course we have to deal with the testing and the benchmark. And the run simple benchmark function, it provides just a controlled environment to test a key feature, basically model reduction, and it simulates a simple generic dynamic system, a toy linear plant, for example, and it generates a history of its states. Then it applies that randomized RSVD technique to this history, showing how the engine can efficiently extract and compress the most important information about the system's dynamics. It also calculates a relative tail error to certify the quality of that compression, and this benchmark demonstrates that the engine's model reduction capabilities are robust, they're effective, and it ensures the system can handle complex data efficiently, so like a biological system would. Then we have some small targeted tests to verify the correct functioning of fundamental mathematics and fundamental physical principles that are embedded in the code. So down here you've got the test make sim pause and logit function down here. This ensures that the functions for handling probability matrices, the make sim pause and the logit SPD functions we looked at before, they have to behave correctly, so we're testing that here. And even when there's problematic inputs, we can change these inputs just to test to make sure that those functions are operating as they should. Then test Stormer-Verlet reversibility. Here we're checking that the core integration method for fast dynamics, the Stormer-Verlet, approximately conserves energy in a simplified scenario, which is the hallmark for symplectic integrators, and it is crucial for stable, physically reliable simulations. Then you've got the test Landauer budget down here. It verifies that the Landauer book is correctly tracking the metabolic costs, and it's enforcing its budget. It's ensuring the energy efficiency mechanisms are working as they're intended. And all of these tests are crucial for the reliability of the entire system. They ensure that the basic physical laws and the mathematical axioms of the simulated biocyber world, all those axioms and laws are upheld. It provides a solid foundation for the emergence of intelligent behavior. So in summary, this Andrecht Neuromorphic Engine version 3 is a comprehensive computational model. It integrates diverse principles from neuroscience, from physics, from machine learning, and it simulates a biocyber agent with hierarchical processing, predictive capabilities, and adaptive learning, and episodic memory, and energy-aware computation. It does it all together, designed with robustness and interpretability in mind. So this is a foundational scaffold that can be built up upon. Of course, we have some more advanced versions of this as well. I'm not showing too much because of the proprietary nature of the advanced versions, but I wanted to give you some idea of the type of systems that we're working on here.